Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to be looking at alkyl halides or halide organic compounds and alcohols. So as usual, we're going to go through naming and writing formulas, reactions, drawing, properties, etc. Through the whole thing. And so let's start with some naming. First of all, when you're dealing with a halide in terms of naming, you're really dealing with a prefix. Whereas when you're dealing with an alcohol, you're dealing with a suffix in order to indicate what is going on. So for instance, with all the halides, you are going to have a prefix of fluoro for fluorine, bromo for bromine, chloro for chlorine, iodo for iodine. Whereas with an alcohol, your suffix is going to be an -al, so the ending is going to be an -al. So for instance, if I was dealing with this one here, I would notice that I have 4 fluorines. And so this is going to be a tetrafluoro. And I have 2 carbons, so this is going to be an eth. And it's a single bond, so it's going to be ethane. So we're going to call this 1, 1, 1. Because this carbon has the most fluorines on it, I'm going to call it the first carbon. And then 2. Tetra, because there's 4 of them. Tetra. Fluoro, because they're fluorine. And so there's my prefix. This whole part here is my prefix. Okay, so tetrafluoro, and then the root to my name is going to be eth for the 2 carbons, and because it's a single bond, it's ethane. Now there's no fancy way of doing the actual formula for this other than just to count everything up. So this would be C2H2. We always put our carbons and hydrogens first. And then it would be F4. Okay, so there's one where it's a structural diagram. Let's look at one that looks like a line diagram. So I do want to focus in and make sure that you understand that there is only 2 carbons here. There is a carbon here, and there is a carbon here. So I'm going to draw those in. There is no carbon on the end of these lines. So a common mistake would be to say, oh, well, I got a carbon here and a carbon here. There isn't. When we end a line diagram with something other than carbon, there is no carbon in that spot. Okay, we're going to talk about that more a couple questions down when we get to alcohols. All right, so again, this thing is an eth and it's an ane, but because there's 2 carbons. But now we have chlorines and fluorines. This is a CFC, a chlorofluorocarbon. This would be used in refrigeration usually, or cooling systems or something along those lines. The same thing of this one above. This would be used in air conditioning units, something like that. Okay, so let's name this one. So we got 3 chlorines, we got 3 fluorines. We're going to call this carbon here number 1. And the reason why, it has 2 chlorines on it. C comes before F, so we're going to call this carbon number 1. And of course we have to name it alphabetical, so it's got to be chloro first and then fluoro second. So I've got a 1, 1, 2, 1, 1, 2, trichloro, 1, 2, 2, 1, 2, 2, trifluoro, ethane. And again, generally the way we do it is carbons and hydrogens first. There are no hydrogens, so C. I've got 2 of them. Then we're going to have in alphabetical order Cl next, so I've got 3 of those, and then F, I've got another 3. So those are both used kind of in the refrigeration industry or in air conditioners, those kinds of things. Alkyl halides or organic halides are man-made. They are not naturally occurring. Okay, looking at the alcohols, I have two here. And again, what I've done on purpose is I've picked one line diagram, and I've also picked one structural diagram. And another thing I did was I picked an alcohol with only 2 carbons. So this one here, because it has 2 carbons, is called ethane. Okay, so it's an ethane, but with an alcohol group. So it's ethane. Now, normally we have to give the location of an alcohol group. But if you have an alcohol group, only one, on a compound that has 1 or 2 carbons, it's always on carbon number 1. So this is carbon number 1, but because it's always going to be carbon number 1, we don't have to say 1-all. So again, this is an ethane 1-all. This isn't that. It's just ethanol. And again, there is no number needed. And what I mean by that is the location of the alcohol group, no number for the location of the alcohol group needed, with 1 or 2 carbons in the main chain. And of course, if there is only one alcohol group. So for instance, if I was to change this into an alcohol group, a hydroxyl group, then there's an alcohol on 1 and there's an alcohol on 2. I would have to call that ethane 1,2-diol. So that's how I picked this next question, is I wanted to do a diol. Okay, so I have to have something that has 2 alcohols, so I know how to name it a bit different. First thing I'm going to do is I'm going to write in my carbons here. Okay, and again, I really want to point out the fact that this here is not a carbon. Okay. And what you'll also notice is this line is a little bit shorter than, a carbon-to-carbon line. Quite often, a lot of organic compound drawing programs will make that line a little bit shorter to emphasize that there is no carbon in this spot. Also, there is no carbon in that spot. That actually is a hydroxyl group, an OH alcohol group. And so we wouldn't include carbons in those spots. So my main chain here is 4 carbons. So this is a butane. So I'm going to write that out. I'm going to say that this is butane. Now normally what we do is we drop that E like above. Like I had an ethane here. Okay, we had an ethane. We dropped the E and then we inserted an all. But there is a weird rule when it comes to multiple alcohol groups in an organic compound. If there is more than one alcohol group, you do not drop the E. So you do not drop this E if there is more than one OH hydroxyl group. So this isn't called butane, it's just called butane. And then I still have to give the locations of the 2 alcohol groups, keeping their numbering as low as possible. So this would be butane 1, comma, this would be the first carbon, this would be the third, so 1, 3, and then because there's 2 of them, you need to have di, so 1,3-diol. So what we're going to do next is looking at drawing a alcohol as well as an alkyl halide. Now normally what we do is we start with an empirical formula. However, when you're dealing with halides, there really isn't a special formula to follow. And so generally what we do is we draw it out and then we kind of count everything up. So we're actually going to finish with the formula. We're going to start with drawing the structural diagram. Now remember, the structural diagram is going to show every single atom and all of the bonds involved. So the first thing I'd point out here is we're dealing with a cyclohexane. So I'm going to draw that first. Of course, it's going to give us a shape like this, which is a hexagon. And then it says it's a 1,2-dichloro. So I'm going to put 1 chlorine here. I'm going to put 1 chlorine here. I'm then going to proceed to fill up all of the carbons to make sure that they have the maximum bonding, which is 4. So this one here has 3. It needs 1 more, so that would be a hydrogen. This needs 2 more, so 2 more hydrogens. And so we just work our way around. Each of these carbons needs to have 2 more hydrogens. And there we go. This one here still needs 1 more as well. And we're going to now do the formula. So starting with carbons, we have 6. And then we'll just go around and count up the hydrogens. So I'm going to start over here. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C6H10. And then, of course, I have 2 Cls. Now, this makes sense. When you have a cyclic alkane, it would be CnH2n. This is a cyclic alkane where 2 of the hydrogens were replaced with 2 Cls. And so when I do the grand total of hydrogens and chlorines, it comes out to 12, which is twice the size of 6. So I know that this makes sense and I'm on the right path. In terms of a line diagram, there would be no showing of carbons or hydrogens, and I simply can go Cl, Cl. Now I just want to point out this fact. Sometimes when we draw it like this, students will forget that there is another hydrogen on each of these carbons, and if they're asked to calculate the formula or figure out how many atoms of each type of element there are, they often forget these 2. So please don't forget that if you were to write out the formula for this compound the way it's drawn, that you remember each carbon has to be bonded 2 more times in order to satisfy the number of times it bonds. The next one we're going to look at here is an alcohol, and so we're going to do all 3 diagrams, a structural, a condensed, and a line. What I do want to point out though is when we're dealing with formulas of alcohols, you can kind of write them one of 2 ways. CnH2n plus 1 OH, so a traditional way it looks, or you can write it without it being the OH together, in which case it'd be CnH2n plus 2O. So it's basically like an alkane plus an oxygen, and the reason for that is the O has an H attached to it. So for instance, I could say this is CnH2n plus 1 OH. And so bute is 4, so I would go C4. H, 2 times 4 is 8 plus 1 is 9 OH. I could do it like that. Or I could say that this is CnH2n plus 2O, in which case it would be C4H10O, and both of those are good. All right, so I'm going to write both of those in. The most correct in terms of the most simplified molecular formula would be C4H10O, but I'm going to put both of them in. So C4H9OH. So let's start with our structural diagram. We're going to put 4 carbons in a row for the bute. We're going to put the alcohol group on the second carbon. It's a 2-ol, so I'm going to go OH. Now, I'm putting this as a kink because if you remember from bonding, this oxygen here has a bent shape because it has 2 lone pairs, 2 bonding areas. It's an AX2, E2 bent formula. And then, but it's not really necessary to add those lone pairs in. It's just a habit of mine. And then I gotta fill up all the carbons to make sure they're bonded 4 times. So there we go. Now let's double check we have all of those hydrogens. So I'm gonna mark this pink and I'm gonna count going clockwise. There should be 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10. I've got 1 O, there's the O, and I've got 4 carbons, 4 carbons. The condensed structural shows the oxygens, or sorry, the hydrogens kind of butted up against the carbons. So for instance, I start with a CH3, that's that guy there. Then I have a CH, that's this one here. And then off of it, it has an OH group, so I'm going to have those together there. and then another CH2 group followed by a CH3 group. So there we go, butan-2-ol. Lastly, the line diagram. I'm simply just going to go up, down, up, 1, 2, 3, 4 carbons. And off the second one, I'm going to draw a line slightly shorter than these other ones. And then I'm going to have an OH group there. And again, the reason I'm drawing it shorter is to emphasize the fact that there is not a carbon in this spot. And that's generally how most line diagrams of alcohols will come. Okay, we're going to tackle the next two sections all in one go here, which is isomers and chemical and physical properties. So we'll start with talking about isomers and general formulas, etc. So when we're talking about alkyl halides, because you don't know how many halides there are or anything like that, there isn't any general rule to follow. Generally, I would draw the compound and I would just add everything up and write it out. When you're dealing with alcohols, monoalcohols, so remember not diols or triols or tetraols, you can use this general formula or either of the general formulas to figure out the number of carbons, hydrogens, and oxygens. Otherwise else, I'm doing the same kind of thing. I'm drawing the picture out, I'm counting everything up if it starts getting too complex. In terms of chemical and physical properties, most halides have dipole-dipole forces, but of course they have London dispersion because anything that has any electrons is going to have London dispersion forces. Now, they will not have hydrogen bonding, and how strong their boiling point and melting point is really going to come down to which halogens are involved, how many are there, etc. So I've written a few notes here. It says, the higher the similar sized, they have a higher boiling point than similar sized hydrocarbons. So if I had a chloromethane, it's going to have a higher boiling point than methane. The more halogens you have, the higher the boiling point for two factors. Usually, it's going to have an increased dipole-dipole moment, or just the fact that most halogens have loss of electrons, and their London dispersion forces are way greater than one hydrogen, and so it increases the boiling point. And of course, the bigger the halide, the bigger the boiling point. So if I was to do something like this, here's methane. We know that this is L-dip only. This would have a way lower boiling point than if I had a chloromethane. Okay, let's call this, we'll do dichloromethane. So this is going to be L-dip and dip-dip as well. So this is London dispersion as well as dipole-dipole. And the reason for that is these chlorines are much more electronegative than carbon. And so the electrons get pulled to this side, and so it's going to be negative over here and positive over here, giving it a dipole moment in this direction towards the negative. So the more polar something is, generally the higher the boiling point is going to be. Now if I did something like this, and this is why I'm saying it's usually dipole-dipole, if I had tetrachloromethane, which is this is actually London dispersion forces only because the dipole moments actually cancel out. They're all moving out towards the chlorines, so it's negative, 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 negative. There's really no positive end to the molecule. However, the boiling point of tetrachloromethane is going to be the highest out of all three of these due to its massive size. There are so many electrons when you have that many chlorines that it causes a really high boiling point. So I'm just going to add this one little note here. Going this direction, you have an increasing boiling point. Okay. Now, when we're talking about alcohols have hydrogen bonding. And I'll show you it to you in two different ways, just using a methanol molecule. So here's a methanol. And so the negative end of the alcohol group really is this oxygen here. So when it comes close to another methanol, I'm just going to draw kind of an inverted methanol here. Maybe I'll do it a different color so you can see the difference. So I'll do this one green. So I'll have HO. Okay, here's another methanol. What happens is these hydrogens here are very, very positive. Okay, the oxygen is very, very negative. And so you can form a hydrogen bond, which is one of the strongest intermolecular forces between two methanol molecules. And so this would be the H bond. I'm going to draw another methanol and show how it interacts with water. So here we go. We got another methanol. And so if it was attracted to a water or put in water, what happens is the water looks very similar there, doesn't it? We have this OH lining up with this OH. Over here we have this OH lining up with this OH. Again, this is going to be positive. This is going to be negative. This is positive. This is going to be negative. And the hydrogen bond is going to be these in this area here. That's going to be your H bond. This makes the boiling point of alcohols way higher than anything else we've looked at so far. Carboxylic acids will have a higher boiling point than alcohols of similar size, which we're going to look at in our next lesson. But these hydrogen bonds are so strong that they have a massive impact on melting point, boiling point, as well as solubility. Now, in terms of solubility, I don't want you to fall into the trap of thinking, well, if it's polar things dissolve polar things, and that's it. Polar water will dissolve polar alcohols up to about 3 to 4 carbons. So I've written this here for you. They're very soluble with few carbons. So up to about propan-1-ol, propan-2-ol. The butanols, you get it to dissolve a little bit. But as soon as you get into kind of 5+ carbons in your main chain, so a pentan-1-ol for instance, its solubility is almost nothing. Because the carbon part of the chain, all those carbons joined to hydrogens, is a nonpolar section, the nonpolar section almost overrides the polar ability of the hydroxyl group, and therefore the solubility in water drops off dramatically. Now, something which you probably will find quite strange is that alcohols are almost infinitely soluble in nonpolar compounds. They're extremely highly soluble in all alcohols. All alcohols are soluble with all nonpolars, with the exception of methanol. Methanol is insoluble with nonpolar compounds because this little carbon hydrogen area here, although it's nonpolar, it's pretty small, and this is just way more powerful. And so the methanols are actually just more attracted to themselves than they are to the nonpolar things, and so they don't want to interact with those nonpolars. But as soon as you hit C2H5OH, which is ethanol, it's infinitely soluble in nonpolar compounds, and all other alcohols beyond this that are monoalcohols, so propan-1-ol, butan-1-ol, etc., they are infinitely soluble in nonpolar compounds. Now, because of their hydroxyl group and their polarity, they have higher than similar polarity or higher melting points and boiling points than alkyl halides and esters, as well as all hydrocarbons. Only carboxylic acids of similar sizes have higher boiling points. Other things to keep in mind, the more hydroxyl groups, the higher the boiling point. So for instance, something like a propan-1,2,3 triol would have a very high boiling point. You can almost add 100 degrees for every extra hydroxyl group. So for instance, if I had 3 carbons with an OH group and I compared that to 3 carbons with 2 OH groups, of course there's going to be hydrogens here as well. Okay. And then I compared it to something that had, say, 3 alcohol groups. Okay. The more alcohol groups you have, your boiling point increases. Okay, and it's kind of roughly, 50 to 100 degrees more for every additional hydroxyl group you add onto the compound. In the final section of this video, we are going to look at reactions that alkyl halides and alcohols undergo. This is the reason why I clumped them together, is due to the fact that they do some similar reactions, especially the one when it comes to substitution and also elimination and how they kind of work together. So the first thing we're going to look at is an addition reaction, which we've looked at already back in our earlier videos. So remember that in an addition reaction, you have to have at minimum a carbon-carbon double bond or carbon-carbon triple bond, and we're adding to it some small molecule. This in turn is going to give something that is less saturated. Now, for the purpose of our course, most of the questions go from a carbon-carbon double bond plus some small molecule into a carbon-carbon single bond, where half of the small molecule goes to one carbon and half of the small molecule goes to the other carbon. And that's what we're going to look at here in this example. So, of course, we're going to have something that is unsaturated to start with. So the most simple unsaturated compound, of course, would be ethene. And so I'm going to draw this out as a structural diagram. So ethene would be C2, ene times 2, so H4. And each carbon is going to have 2 hydrogens. Now, my small molecule is going to be a water molecule. Whenever I write out my water molecule in a addition reaction, I always like to write it out as HOH, because that's how it behaves. That's how it reacts. It's almost like you have a hydroxyl group and a hydrogen atom. And so what will happen is 1/2 of each of this small molecule, in this case water, will go to each carbon. So I'm going to say this hydrogen goes to this carbon, and this hydroxyl group, I'm going to call it a hydroxyl group, goes to this carbon. Of course, it's not really a hydroxyl group in a water molecule. This is a molecule. It's covalently bonded. It's not independent. But I'm just going to call it a hydroxyl group for the purpose of this reaction. So if I draw out my product, I'm going to color code it here. I now have a single bond between the carbons because this bond has to break, and then each carbon would take 1/2 of that bond, or 1 electron in that covalent bond. So this would be the pi bond that would break. And so here's what I started with in terms of ethene, but now each of them has 1 more electron to bond, and so one of them is going to bond with just the hydrogen atom, and the other one is going to bond with the other carbon atom here. And so now what I have is ethanol. Now, if you had a larger unsaturated compound, let's say like a propene, you may end up with a propan-1-ol or a propan-2-ol, or a combination of both. As you move forward in organic chemistry, you look at which one is more likely to occur, or which one's going to happen in more abundance, or which one is only going to occur. But for right now, we're really just looking at some very basic addition reactions. The next one we're going to look at is a substitution. Now remember, we called substitution 1 in, 1 out reactions. And what I mean by that is one important atom, or in this case it's going to be a hydroxyl group, is going to switch places with another one. And so the example I picked was ethanol reacting with hot ethanol reacting with hydrochloric acid. Now generally in a substitution, and I'm saying this generally, what you're going to be substituting out is a nucleophile. And a nucleophile is a very electronegative atom or group of atoms. And so in our question here, and I'm going to do, again, I'm going to color code this. We have two nucleophiles, okay? So our first nucleophile would be the hydroxide. It is a very electronegative group. The oxygen is extremely negative. Our other nucleophile here is chlorine, okay, which is much more highly negative than the hydrogen here. Now, we're not talking about any specific reaction mechanisms here. This is very generic. So again, if you look up kind of substitution reactions in higher level textbooks, they're going to talk about different types of mechanisms. We're just talking this at a very basic level. So again, this is quite negative. This hydroxyl group is quite negative, okay? And so they're going to swap out with one another. So this Cl is actually really attracted to that C there. So it's going to bond with this C, and in doing so, the C is actually going to kick out the hydroxyl group, which will then swap out with the Cl. So now what we have is HCCCl, and we formed an alkyl halide. And I'm going to make that red. And the byproduct here is going to be HOH, which is simply water. So one nucleophile has substituted out for another nucleophile. Whenever you have a one-to-one swap out, this is called a substitution. Let's name this product. This would be chloroethene. And I'm not going to say 1-chloroethene. I could, but the assumption here is going to be that the functional group is going to be on that first carbon. So chloroethene or 1-chloroethene, and then of course water. In our last two reactions, we're going to look at elimination of alcohols into alkenes and water, and we're going to look at the elimination of halides using some kind of base. And generally this is done in ethanol. The first one we're going to look at isn't too complicated, and again I'm going to stick with something fairly simple in terms of alcohol. So we'll stick with ethanol, and so this is called a dehydration reaction, and essentially what happens is, under the right conditions, you're able to remove this hydroxyl group. And in order to do that, you would actually have to remove a hydrogen on the adjacent carbon. So any of these three on the left-hand side, I'm just going to pick this one, okay? And so it's called a dehydration because we're removing essentially a water. So if this hydrogen joins with this hydroxyl group, we're of course going to get water. So that's why it's called a dehydration. By doing so, each carbon will have one electron to then make a pair. And so it will pair by making a pi bond, which makes up a double bond, turning this into an alkene. This reaction essentially is the reverse of the one we've done on the previous page. So again, in an elimination, what you're doing is you're starting with a carbon-carbon single bond, which is saturated, and you are turning this into something which is unsaturated. Now, for the purpose of our course, we only talk about saturation in terms of carbon-carbon bonding. As you move into higher level chemistry, you'll start talking about degrees of unsaturation with halides and hydroxyl groups and stuff like that. But again, for the purpose of our course, a carbon-carbon bond is all we're focusing on in terms of being saturated or unsaturated. So all carbon single bonds, carbon-carbon double bond, Carbon-carbon single is unsaturated, carbon-carbon double is unsaturated. So in an elimination reaction, you're always going to make something which is unsaturated. Okay, the last one we're going to look at is a little bit more complicated. It's the elimination of a halide to an alkene using a base. Now, this kind of looks like maybe it's going to do a substitution, but it isn't. And I'm going to use something like, let's call it 2-bromopropane. Okay, so we'll have this, and I'm going to put some hydrogens in here so you can see what's going on. Okay, so in a elimination of a halide to an alkene, you have to have a strong base or a ethoxide ion. We're not going to talk about ethoxide. We're going to use sodium hydroxide. And in this process, what is going to happen is a hydroxide, in this case the OH minus, and I'm going to have this break off because this really isn't going to stay together. This will be a sodium ion and a hydroxide ion. What it's going to do is it's going to go to this carbon here, and it's going to steal this hydrogen here, and I'm going to color code this an H. And in doing so, it's going to remove the hydrogen and form a water. So now what we would have is an HOH, which would be these ones here. Okay. Now what happens is this carbon has a loose, a lone electron here. And so this carbon here ends up kicking off this bromide, wanting to make a double bond, because of course in an elimination we are going to form a multiple bond. So this hydroxide group, it's not hydroxyl, this hydroxide, which is a base, that's what we're saying, using a base, is actually going to take a hydrogen away from a neighboring halide joined carbon. This is going to form water. This carbon is now going to kick that bromine off, and it's actually going to turn into a bromide. So again, I'm going to color coordinate this. I'm going to say that this is Br. This gets kicked off, and it's going to take both of these electrons to form Br minus. So I'm going to add that to this side, Br minus. This H here, when it left with no electrons, and so now there's 2 electrons in this area, which can form a double bond. So the sodium is still there. I'm going to add that in over here. I'm going to say the sodium is still kicking about, but the most important product is really what is remaining of this 2-bromopropane. What we're going to have is a double bond between those 2 carbons, like this, and we have now formed a propene, which of course again is necessary in an elimination, that we go from something which is saturated in terms of carbon-carbon bonds to something which is unsaturated with a carbon-carbon double bond. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.